Nuclear power plants remain largely misunderstood by the general public. Beyond their portrayal in television shows and movies, few people truly understand how they generate electricity or where their immense energy comes from. This video explores how a nuclear power plant works, from the physical principles behind nuclear energy to the process of converting atomic energy into electricity that powers millions of homes. The story begins in 1934, when Italian physicist Enrico Fermi conducted experiments by bombarding uranium with neutrons. His goal was to create heavier elements, but the results were unexpected and difficult to explain. Several years later, Otto Hahn and Lise Meitner revised these experiments. They discovered that uranium nuclei could split into smaller elements, such as barium, while releasing additional neutrons. This finding led to the understanding of nuclear fission, a process capable of triggering chain reactions and releasing enormous amounts of energy. This discovery marked a turning point in history. It first enabled the development of nuclear weapons and later paved the way for the peaceful use of nuclear energy through nuclear power plants. Every atom consists of a nucleus made up of protons and neutrons, surrounded by electrons. Inside the nucleus, powerful forces act simultaneously. Some tend to push particles apart, while others hold them together. The stability of a nucleus depends on its bending energy. Light elements can release energy by combining, whereas very heavy elements can release energy by splitting apart. The element iron represents the point of maximum stability, possessing one of the most favorable binding energies per nucleon. As a result, nature relies on two fundamental processes to reach more stable energy status. First, nuclear fusion, the combination of light nuclei to form heavier ones. And second, nuclear fission, the splitting of heavy nuclei into lighter ones. Both processes release far more energy than ordinary chemical reactions. The most commonly used fuel in nuclear reactors is uranium-235. When a neutron collides with a uranium-235 nucleus, the nucleus might split into two smaller fragments, releasing energy as well as several additional neutrons. These newly released neutrons can then trigger fission in nearby uranium nuclei, creating a chain reaction. If this reaction occurs uncontrollably, it can lead to a nuclear explosion. However, if it is carefully rigged, the released energy can be safely harnessed inside a nuclear power plant. Although uranium is relatively abundant in nature, uranium-235 accounts for less than 1% of natural uranium. Most uranium consists of uranium-238, which is not as suitable for sustaining a chain reaction. For this reason, nuclear fuel must undergo an enrichment process that increases the proportion of uranium-235. The enrichment level used in power plants is sufficient for electricity generation but remains far below the levels required for nuclear weapons. Another important factor is that slow-moving neutrons are more likely to introduce fission. To reduce neutron speed, reactions use moderator materials such as water or graphite. Now let's talk how a nuclear power plant works. Pressurized water reactors, the most common type of nuclear reactors worldwide, contain nuclear fuel inside a large vessel known as the reactor vessel. Water circulates through the reactor under high pressure and serves two essential purposes. 1. Acting as a neutron moderator. 2. Removing the heat generated by nuclear fission. The system is known as the primary circuit. The heat produced in the primary circuit is transferred to a secondary circuit through steam generators. In this secondary circuit, water is converted into steam, which is then directed toward turbines. The steam causes the turbines to rotate at high speeds. These turbines are connected to an electrical generator, which converts mechanical energy into electricity. Transformers then increase the voltage so that the electricity can be efficiently transmitted through high-voltage power lines. After driving the turbines, the steam must be converted back into water so that the cycle can continue. This process takes place inside a condenser, where the steam is cooled by a third water circuit. This cooling water is typically obtained from nearby rivers, lakes, or the sea. Once the steam condenses back into liquid water, it returns to the secondary circuit and is pumped back to the steam generators, completing the cycle. In conclusion, nuclear power plants generate electricity by harnessing the energy released during the controlled fission of uranium atoms. Although the underlying physics is complex, the overall objective is straightforward: produce heat, convert it into mechanical motion, and then transform the motion into electrical energy. Through this process, nuclear power plants provide a reliable source of electricity for millions of people and remain one of the most significant energy technologies in the modern world.